Welcome to lecture 37. So, we will continue with procedural abstraction. So, as I said, one thing is that the whole purpose of abstraction is that you can take any semantically meaningful syntactic category and you can use it as a body of an abstract, and an important part of using it as a body of an abstract is to give it a name. So, essentially when Shakespeare asked what is in a name, the answer should have been an abstract, but he apparently did not get that. So, so you have various kinds of abstracts, expression abstracts which we have already actually seen partly, procedural abstracts which are command abstracts, and then you have definition or declaration abstracts as in Modula, ML, C++, Simula, Smalltalk, etc. Right. So, the most important features of an abstract are really its name, and of course, we have to answer the question what exactly is an abstract. That is an important semantic issue that we have not yet addressed, and of course, the parameters to capture similarity of computations and so on and so forth, and a type checkable body which is elaborated whenever the name is, so to speak, called with appropriate parameters, right. So, we were concentrating on control abstraction, and what I say for control abstraction, namely procedures, more or less also holds for these expression abstracts, where the expression abstracts denote functions. Anyway, when we do the semantics of ML like functions, we will come to that, but let us look at this, the form of control abstraction that we have got, which is basically like functions in Pascal or procedures which change state in some fashion. And of course, when it comes to these kinds of abstracts, normally there are two kinds of scope rules that you might use. One that we have been using mostly in languages like Scheme, ML and Pascal, C, Ada, Algol 60, most of these languages, actually most of the languages which are compiled rather than interpreted, though of course our ML environment is an interpretive environment, but most languages which are compiled prefer to use a static scoping mechanism, which is which means that it is easier to debug, look at non-local references from the text of the program rather than from the runtime environment. So, the bindings are all compile time, or the identifiers are all statically bound. So, and the main difference between in the case of dynamic scoping, what it means is that non-local references, as in this case where you have a chain of calls, assuming this large program P has two procedures P1 and P2 which are at the same level of nesting and independent of each other, and within P2 there is a call to a nested procedure P21, within P2 there is a call to this independent procedure P1, and within P1 there is a call to its own nested procedure P11 which has, let us say, a non-local reference. So, if it were a statically scoped language, this non-local reference would refer to a binding occurrence that occurs in the innermost textually enclosing block. On the other hand, in a dynamically scoped language, this reference would actually depend on this calling sequence and would refer to the most recent calling block, most recent invocation of a block which actually contains a binding occurrence. So, that would be the difference between static and dynamically scoped languages, and the reason I said that dynamic scoping is mostly used in an interpretive style rather than in a compiled style is basically this. So, is basically because of the runtime environment. So, let us look at that, let us look at this program executed in which is let us say at this point at some control point here after this chain of calls. So, if you look at the runtime stack of this program, runtime, I am not talking of compile time. So, if you look at the runtime stack, the activation records actually look like this. So, firstly of course, you have a global environment. This is sort of normal since no program usually works without a global environment. You usually require some global environment which contains standard I/O procedures, maybe libraries and so on and so forth. So, let us assume that there is a global environment in which every program executes. And then of course, there is this call to this procedure P1. There is this program P which has a pink border or a purple border if you like, this program P. So, the activation record for this program P, which actually, well, it has a local declaration of a variable x and it has of course the procedures P1 and P2 declared locally. Okay. So, in the process of compiling, what would actually happen is this P1 and P2 would refer to would refer to the jump addresses to the code segments of the appropriate procedures. Okay. So, the fact that P1 and P2 are local to the program P means that you have to somehow create a jump address, the address of the code segment, and in case and then P1 and P2 could have parameters. So, in any call within P to P1 and P2, you will have to type check parameters. So there will be also part of this would also be some information on the kinds of parameters in the order in which they appear and their types. I mean they are basically their types. So that any call to P1 or P2 when you are actually compiling this main program should type check, right. So, anyway, so in the runtime environment, this P1 and P2 would refer mainly to the code segments of P1 and P2 where they are where the jump addresses are, I mean where the code starts from. Okay. So, from within P of course, there is a call to P2 which is this green block, and so there is an activation record for P2. P21 is of course nested within P2, so therefore, there has to be some address to its code segment, and there is a local variable x, and there are of course parameters. This is a main program, so it does not have any parameters. Strictly speaking, main programs also have parameters which usually refer to something in the library routines, like you have like a Pascal program actually refers to the files that it is going to access, but let us assume that there are no such things. So, a procedure usually has some parameters, it has local variables, maybe locally defined procedures the address of whose code segment you require to maintain, and then within from P2 there is a call to P1. So, there is an activation record for P1 which is similar, right, and from P1 there is a call to P11. So, there has to be an activation record for P11. So, the typical runtime environment at the point when you reach this control point is that there are 4 activation records here. I mean the calling chains of length 4 besides the global environment. So, now what happens is this: every time the moment, for example, the moment you stop executing P11, for supposing the execution of P11 is completed, then what happens is you are back in the environment of P1, which means that this is the current environment pointer. Okay. So, you have to know at each stage what is the new environment pointer that you have to jump to when you exit this scope during execution. So, when the scope P11 is exited during execution, then this top block, this top blue block should go, and your current environment pointer should point to the bottom of this, right. So, the fact that you are creating a new little environment at each stage means that you have to have what is known as a return pointer, which will return you to the current, to the new current environment pointer each time you exit a block at execution time. During execution, the moment the block P11 is exited, you require a return pointer which gives you the base address of the previous activation record. Okay. So, this RP is called the return pointer, right, and this, whether your language is a dynamically scoped language or a statically scoped language, you require these return pointers each time, right. So, so what is called the dynamic chain, which is really the calling sequence looked at backwards. Okay. If you remember the calling sequence here, so this is really the dynamic chain, right. So, there is this calling sequence. So, you have a dynamic chain which points from P11 to P1, P1 to P2, P2 to P, and P to the global environment if necessary, but I have not shown that. So, essentially you require this dynamic chain which is maintained at execution time. So, now in a language that is interpreted, it is easier to implement a dynamic scoping mechanism. For the present, assume that this is not there. In a language that is dynamically scoped, what it means is that every time you see a full phrase, you translate it and execute it before you look at the next syntactic phrase. Okay. So, now what happens is, supposing you see this phrase containing this non-local reference to, this blue reference to x, then when you have to translate it, you have to check out whether you have it, you can just traverse down the dynamic chain to find out some reference where, find out the first reference where x was actually declared or where x has a binding occurrence. Since translation and execution both take place simultaneously at the same time, essentially the most of the basic information about identifiers and their bindings and so on will still have to be maintained in a symbol table at runtime. Since there is no compile time, each phrase is textually read, translated, code is created and executed. So, whenever you read a new non-local reference, you do not know anything about it till you traverse down the dynamic chain. Either you have it in the current environment, or you have it in the previous environment, or you have it in the previous environment, and whichever is available, you just, whichever is the first that comes, you just bind it to that, right. So, under a dynamic scoping rule or with dynamic bindings, that means all the translation is done at execution time. I mean, there is no separate compilation phase. Then what happens is that with just this dynamic chain, the innermost enclosing invocation which contains a declaration of that non-local reference can be found by just traversing down this chain and searching through the subsequent activation records. So, if you have a non-local reference, what makes it a non-local reference is just the fact that there is absolutely nothing corresponding to this activation record which contains a declaration of x or a specification of its type. So, what do? You go through the previous invocation, which is P1. You check whether P1 in the activations of in the activation record of P1 there is some identifier with a declaration for x. If there isn't, then you just traverse down from the return pointer of P1 to the previous thing and check, and you will find maybe this x, there is an x declared here. Okay. Remember that all the symbol table information, the identifier, name, its type, everything has to be stored, since it is interpreted, it has to be stored somewhere at runtime. So identifying that it is an identifier with a certain name is possible at runtime, provided you do everything at runtime. In a compiled language, identifiers and names no longer exist after compilation. They have all been translated into addresses. Okay. So, there is no question of string matching identifiers and so on and so forth. So what in a dynamically scoped environment, you just keep traversing down this dynamic chain in order to find the most recent binding occurrence that was encountered in the chain of calls. Okay. Right. On the other hand, so this dynamic chain actually serves all this purpose, which is the reason early implementations of Lisp and APL, which wanted to make it interpretive, which is also an easier thing to write, actually use this dynamic scoping mechanism. But what it means textually when debugging a program is that you cannot look at an abstract, you cannot look at a procedural abstract in isolation and hope to get anything out of its non-local references. The only way you can understand that abstract is by essentially hand executing and producing the appropriate calling chain by hand execution, and then determining what would have been that reference at that point. What would have been the binding occurrence for that non-local reference at any point. Yeah. So, debugging is interactive debugging may be easy, but a planned debugging of the text is usually quite hard with a dynamic binding mechanism, right. So most languages which allow for compilation and ML and Scheme, because they actually would like to encourage debugging from a text, they implement what is known as a static binding mechanism, which means essentially the kind of binding mechanism that one sees in Pascal, right. But then what does this mean? This means that in the runtime environment, you have to maintain what happens in a compiled language. This is specific to compiled languages. At compile time, a symbol table is created and an address, a relative address relative to some base for each identifier is created. And what is the translation of an identifier? Let us say of a simple variable, an identifier which denotes a simple variable is just the translation of replacement of that name by its appropriate relative address with a reference to the scope in which it was bound, right. So, which means that now under a, so in the process of compilation, I can actually create an address for this with a depth of nesting some let us say 1 and a relative address, which basically says that this has been allocated so much of memory, so many bytes from the top of the base of from where this scope starts, would start in the activation record in the runtime, right. So now any non-local reference x here would therefore refer to just this address with the appropriate nesting depth with the same relative address, that it is actually a reference to this x, right. So as you read through, as the compiler actually scans the token file and it encounters this identifier x, it just hashes on to some binding occurrence and translates this x by the appropriate address. Okay. So, at the code that is actually executed only has addresses, relative addresses, which at execution time the bases will be filled up, as and when activation records are created there will be a base address stored somewhere, which you have seen in the PL0 compiler. I mean there is a base on the stack for the current activation record, and all addresses are relative to how much above that base should you go before you reach this variable, right. So, what this also means is that since you have addresses which are relative to a base, in the case of the runtime environment you have to maintain the static structure of the program somehow. I mean you have to maintain, for example, the fact that both P1 and P2 are nested within P. So, P1 is this red activation record, it has a pointer to the pink one, this green P2 is this green one which has a pointer to this pink one, and this blue P11 is nested within P1. So, there is a pointer from the blue to the red, to the base of the red. So, that now if you can maintain this information, then all non-local references which have a nesting depth comma relative address given to them means that you go down the appropriate chain, this appropriate chain rather than this chain. I mean you have a current nesting depth of some, let us say 2, and you have a non-local reference x which you have a current nesting depth of let us say 3, P11 is at nesting depth 3, and you have a non-local reference which has been translated as having nesting depth of 1 and has so and so address relative to that base of that nesting depth 1. So, which means that you have to traverse down 2 steps and go up to the appropriate translation above the relative address in order to access x, right. So, this chain of nestings, textual nestings is what has to be maintained in the runtime environment if you have to have a statically scoped language implement, especially a compiled language, right. So, a typical a typical language with dynamic binding will just have this kind of will just have a dynamic chain. If it implements static binding, then it also has to have a static chain pointer, which essentially captures the nesting levels and the textual containments of the various blocks, right. So, essentially the difference is that in a dynamically scoped language the free or the non-local identifiers are bound in the environments of invocations or calling environments at runtime, and of course dynamic binding is therefore much more easily implemented in interpreters. You just have to follow the return pointer chains. So, this going back to this diagram, let us just this SCP stands for the static chain pointer, this RP stands for the return pointer. Once this invocation is over, what is going to be the current environment pointer or the base of the, what is going to be the new current activation record and what is it's going to be its base address. So, that you get from here. So, essentially when you exit this block, this return pointer, the value in this location is going to be copied into the current environment pointer, and the value in this is just the address to this base, and so your current environment pointer will be pointing to this, and all addresses will that you will be referring to will refer to addresses which are either which are anywhere less than this. So, you do not need to explicitly garbage collect it. With further invocations, all the previous activation records which are really not supposed to be active, but have been left behind as deadwood, will get overwritten, right.
So this P1 and P2 are pointers to the we have elaborated P1 and P2
right.
the main program. So where are we elaborating P1 and P2?
You have under either a static or a dynamic scoping mechanism, when you actually read P1, you will be actually creating its code segment somewhere, and it is going to be a pointer to that code segment, right. Mostly it is going to be a pointer to that code segment. Very often, if there are procedures with parameters, what happens is that you often, for type checking purposes, you do not want to put all the information about parameters. Basically what you want is type information and the order of the parameters, right. You may not want them all to be all located here. What you might do instead is have each procedure, since different procedures can have different numbers of parameters with different kinds of types, what you might do is you might standardize it to 2 pointers. One is an address to a code segment, another is a pointer to some place where the sequence of parameters and their types and whatever information you might want to include about their types is maintained, so that you can do the type checking, right. So, it is some record which basically allows you to find the code segment of that procedure if you want, right. So what it means is that under a static environment, under a static binding mechanism, as you compile, which is normally a compiled language, for a compiled language, as you compile, as you read the token string after lexical analysis, basically it is a token string, you actually maintain for each block that you have created a nesting depth, its the addresses for each of its variables. Variables are going to be translated by addresses, right. So, the symbol table variables are going to be translated. So, the symbol table contains type information, address, size, this, that, such things, right. So, at compile time you have these symbol tables for each of these, and as you textually read the program, you actually create all this information that is essential. The moment you exit after compiling P11, the moment you have exited P11, this part of the symbol table is no longer necessary, and you work with this part when you, especially when you are reading the body of P1, right. And once you have finished reading the body of P1, then this part also goes away. The next textually available thing is the procedure P2. So, a new symbol table for P2 is created, let us say green in color, and then within P2 there is the procedure P21, let us say black in color, and as you read P21 you create another symbol table for P21. The moment you exit P21, the symbol table for P21 is removed and you are left with the symbol table for P2. The moment you have finished elaborating, generating the code for P2, which essentially means you have finished reading it and generating code, P2 goes away, and then you are back with just this, which is the main body of P of the program, and you can elaborate the program, and all references in the program could, of course, the symbol table here should also contain some information saying that there are these two procedures P1 and P2, right, because in the main body of P you can have calls to P1 and P2 which have to be somehow type checked, and similarly in P1 you should have some reference to the procedure P11, because you can have calls to P11 and you are required to do type checking, right. So and the way you would create addresses is that at every point in the symbol table you will actually maintain what is the current nesting depth that you are looking at, and for each identifier essentially something the current nesting depth is going to be equal to the length of the static chain which is going to be maintained at runtime, right. So, it is just so any reference to a non-local variable or even to a local variable will be the chain position and a relative address corresponding to the base of that activation record, right. So, these static pointer chains will have to be explicitly created and maintained in order to capture this innermost textually enclosing block information to resolve non-local references, to resolve both local and non-local references. It is a uniform procedure. But of course, what happens in a dynamic environment is that sometimes, so what it means is that, let us get back to this diagram. So, what it means, actually let us get back to the suite of diagrams, right. So, now at this, so if you look at the static chain pointers, if you look at this, there are actually two different static chain pointers which of course meet at the main program. They are two completely independent. One is this green single pointer chain and the other is this double pointer chain, right. Okay. So, at any point during the execution of the program, the only references, I am assuming a statically scoped language, the only references you can have to identifiers are identifiers in the current activation record, identifiers in the activation record immediately pointed by the static chain pointer, or identifiers of the activation record pointed down by this, by the static chain pointer of this static chain pointer. So, what I mean is the only references you can have in this blue procedure are to identifiers in the blue procedure, in the red procedure or in the pink procedure. You cannot have any references to identifiers in the green procedure under a statically bound condition, under a static binding mechanism. Okay. Now, you can think of it, if you just generalize this diagram so that you have lots and lots of procedures P1, P2, P3, P4, P5 all at the same level and all of them having very deep levels of nesting with more and more procedures embedded in them, then your runtime stack in some when it is executing some piece of code in the innermost nesting of some procedure can actually have a whole lot of pointers, a whole lot of static chain pointers which are all independent except for the fact that they meet at the main program. Okay. And at any time at the from the top of the stack in the activation corresponding to the block which is being executed, at any time the only non-local references are going, so that you actually have a collection of disjoint chains. I mean, they are not disjoint because they all meet at the main program, but otherwise they are all disjoint. So, at any point you actually have a huge, you might have a huge collection of static chain static chains, of which at any instant only one static chain is really necessary for your access in order to access non-local references. Okay, you could have a huge number of independent static chains, but at any instant there is only one static chain that is actually useful to you for executing that block, right. Is it clear? I mean, here the example is that there are two independent static chains, and at this point this static chain is the only thing that is necessary, right. If you consider a nesting mechanism, if you consider a nesting mechanism, a calling mechanism for this same program, such that you actually you call P2, and then you call from P2 there is a call to P21, and from P21 of course there could be a call to P1 and there could be a call to P11, okay. Then you would have two independent static chains, okay, and depending on which block you are executing, you require only one of the static chains to be available for that block. That is the only static chain that is useful for that block. The moment you exit that block, you might move into a different block which is not textually nested, which means you will require a different static chain pointer, right. And in languages where there is a huge amount of side effects, like most imperative languages, what it means is that a lot of people, instead of having a huge number of parameters for their procedures, they tend to use a large number of globals, okay. In that case, for a really complicated program, what it means is that traversing down the static chain for each and every non-local reference can become expensive and can slow down execution, right. So, at any point what happens is, so very often some speed up mechanisms are used, and one speed up mechanism is the use of a display, right. So, so a display is just a collection of registers, high speed registers, somehow organized logically in the form of a stack, which you use in some order, okay. And since out of a vast collection of disjoint static chains, at any point you require only one complete static chain pointing down up to the main program, these static chain pointer addresses are all stored in the display in a last in first out fashion, okay. So, the address, the base address of the pink block will be stored here, and then the base address of well, the green is not important, the base address of the red one would be stored here, and the base address of the blue one would be stored here, right. So, as long as you are executing this blue block, these are the only base addresses you require in order to resolve non-local references fast, okay. You know the nesting level, textual nesting level here is 3. If you find a non-local reference at nesting level 1 or some such thing, then all you have to do is look at the base address given here, 2 down this display stack, and look at the relative address starting from this base address. Just imagine if the stack actually grows and you have a reference to a global variable at nesting level 20, that means you will be doing 20 hops down the static chain before you can locate, before you can access that non-local variable. And you do not want to do that 20 hops, you might, that entire procedure or that function might have no parameters, nothing, it might just be doing some task which is completely modifying global variables, which means for each global variable occurrence that is there, either for modifying it or for reading its value, for each of those global variables you will have to make 20 hops down this static chain and then find the address and either modify it or read the value, and you do not want to do that. It can slow down your execution tremendously. So, by the use of this display, what you can actually do is you can just subtract nesting levels from the current nesting level, go to the appropriate go to the display to find the base address and find the relative address from that base, right. So, essentially what we are saying is that this this pink actually contains the address of this base address. This pink base, the address of this base is actually given here. Similarly, the address of the red base is given here, the address of the blue base is given here, and these are high speed registers, right, which make it which make accesses fast. Anyway, that's a sort of an optimization or a speed up, if you like. It's nothing more than that. So the act of naming essentially does this, and which means that what it means is that in the case of a dynamically scoped language, there are enough overheads just translating it at runtime, translating the phrases at runtime and accessing them. But you do not have this extra overhead of a static chain. You just keep following the return pointers which form the dynamic chain every time you want to get to resolve a non-local reference. Yeah. So, there is an extra overhead with static binding, but then that extra overhead means that debugging your program is easy. It is possible to compile programs, use them for production runs, whereas an interpreted programming language basically means that you will be doing on the fly, not really debugging, you will only be doing on the fly redefining, on the fly development, which may not be systematic, which could be quite ad hoc. So, the extra overhead is worth it provided we can somehow speed up global accesses, and speeding up global accesses means using some method by which pointer hopping can be saved somehow by using a fast access. So, supposing you have got a nesting level of I do not know 60, 20 or something, you may not actually have that many registers, but let us assume you have cache, which is a fairly high speed memory mechanism. Then you can access the cache, but the point is that you are at a nesting level of 16, you got a global variable at nesting level of 1 and you want to find out its address. You do not have to do 16 hops down the static chain, you just have to go to the cache 15 places down, random access, because this is going to be organized as an array if you are going to organize it in cache. So, it is all going to be, this is all just addresses, so they are all uniform, right. So, you do not have to, you can actually randomly access the corresponding base address, go back to the runtime stack to that base address and take the relative address from that. So, your access speeds are substantially improved when you use a display mechanism, and hopefully your execution will improve.
Directly going to the 15, directly going to that 15. How do you find that X is what's the address of that X?
That X at compile time, that X has been translated into something which gives the nesting level and relative address from that, from whatever is the corresponding base. So, you have the nesting level. I mean, that's the job you are doing at compiling. While compiling, what are you doing about non-local references? You are replacing all identifiers by a nesting level come relative address with respect to the base of that block. Okay. So, your main problem at runtime is finding the base of the block, the relative address is there. And how do you find the base of the block? It so happens that the difference of the nesting levels is just going to be the length of the static chain pointer, the number of hops down the static chain that you have to perform. So, instead of doing that number of hops, you actually organize that static chain itself as an array in some high speed memory, so that you can randomly access that. So, each time when your static chain changes, there is this extra overhead that the new static chain will have to be copied out into this display, right. For example, here the moment I exit this blue block, okay, on exiting this blue block, I am not traveling, I am not going back to an activation record which is along this same static chain path. I am going into an activation record which belongs to a different independent static chain. So, the extra overhead when I lop off this, when I exit this blue block and come to this red block, is that I have to completely erase out my display, and now before executing this red block, before continuing with my execution of this red block, what I have to do is I have to copy out this static chain into the display to enable quick accesses to non-local references in this red block, right, in the code segment of this red block.
But sir, in the first case it could narrow down to actually traversing the chain.
In each case it is actually, it could, for example, yeah, when you go from here to here it just works out to that, but I can't be, I mean, but that is not something you can, that can really be guaranteed, right. I mean, you have to at least do one traversal down this, the appropriate static chain fully before you can decide what to do. And it is easy to do that blindly by just copying out the display every time you exit the block and enter a new block. So, every time, so when I exit this blue block and come here, I look at the static chain pointer, copy it out into a display in a reverse fashion, and then traverse this, copy out its static chain pointer, and so on. Yeah, that's really what I am going to do. But every time I exit a block and get back into some previous invocation, I have to do a complete traversal of the static chain at least once. But what I am claiming is that is all you have to do, right. Then you can save on subsequent hops in through a static chain by using a display, right. Right. So, and now of course, when it comes to, and the thing is that we have actually, we are now looking at pragmatics before semantics, because a lot of the pragmatics is very easy. I mean, the act of naming has not significantly changed implementations, and in the case of recursion it is even trivial. I mean, one important thing about naming I said was to provide a form of abstraction. An important feature of that kind of naming as a form of abstraction is also that it allows you to call recursively automatically, right. So, for example, in an unnamed block, except with explicit go to statements, you can't go back to the beginning of the block from within the block. With naming you can automatically make recursive calls, and the whole point about implementations, once you have organized your runtime stack in this fashion, okay, you should throw your mind back to the runtime environment in languages like Pascal and ML as opposed to runtime environments in languages like Fortran. Okay, just briefly recalling what we did in Fortran. In Fortran, every block was independent of each other and they were all statically allocated in memory, okay, and they all contained persistent data, and any reference had an absolute static address, okay. And one consequence of that, so for example, if you were to take our diagram in a Fortran like environment with static allocation, what it means is that there is going to be a pink block code segment cum data separate from I have forgotten the color of P1, red. P1 is going to be code segment and data. P2, the question of nesting of course never arose, so let us assume P11 and P21 do not exist, okay. P2 would have code segment and data, and they would all be fixed for life, and by life I mean the lifetime of the program, right. So, what it meant was that all references, whether local or non-local, would have a fixed absolute address which is relative to the address given at loading time of the program, relative to some base given at loading time of the program. So, what that means is that you can't have recursive calls, because recursive calls means having different copies of the same activation record with different values and so on and so forth. So, you just can't have recursion. On the other hand, with the kind of runtime stack environment, but on the flip side of the coin is that it is also very fast. Having fixed it all, Fortran programs execute extremely fast because they do not have these complications of allocating fresh at runtime, deallocating, traversing pointers, there are none of these hassles. So, the executions are very fast. One reason why scientific programs are still written in Fortran. The other important reason of course is that lots of them were written in Fortran and nobody people are feeling too lazy to change it. Okay. But the moment you allow for recursion, the moment you have organized your runtime environment as in the form of a stack with a dynamic allocation of memory, of activation records and so on and so forth, you directly open up and make it flexible for the purpose of implementing recursion. So, what it means now is if there is a recursive call, so if there is a recursive call, you have this program here and then there is another sub program here which is recursive, then what it means is that your activation record would really look like something like this. For over n calls to this subroutine, what you will have is essentially one activation record for, well, here are the globals, let us say the global environment. You will have one activation record for the main program, which with a return pointer, this is a main program, so there are no return pointers and no static chain pointers, and then you have several activations of this recursive call with a static chain pointer pointing here and a return pointer pointing here. And then let us say there are 3 activations of this, you are assuming the case when the recursion has been called thrice, then you will just duplicate these static pointers like this and your return pointers will be like this. So, you can have several incarnations of the variables. Local references will be locally resolved, non-local references will go down the static chain. When you exit one invocation, you automatically have from the return pointer the address of the next of variable, the invocation that you are returned to, right. And so, there is absolutely no problem with the implementation of recursion in this case. Of course, then the next important question is what exactly do we mean by meanings when you have functions, and we will worry about that next.